All right, everybody, today's video is completely factoring polynomials using a series of tools to go from standard form to factored form. It's gonna be a long one, so let's get after it. Busy, gotta go. So, completely factor each polynomial, that is, write each standard form polynomial as a product of irreducible linear factors. We'll talk about that word later, but basically we're saying we want to write it in factored form. So we're going to use a series of tools to do that. I probably won't end up using factor remainder theorem, but I'll use the rest of these. So it's going to be a long video. Let's start. Start with f of x. First thing we're going to do is, we know we're going to do synthetic division. Synthetic division is the biggest tool. So I'm just going to start by getting synthetic division set up, because that allows me to do my quick check of factor remainder theorem. Remember, factor remainder theorem says you can check if something is a factor by plugging in the 0 of the divisor. And it's really helpful for checking x minus 1, because 1 is easy to plug into a standard form polynomial. If you plugged in 1 here, you would just get the coefficients, so you could add them. Here, if we add the coefficients, we get 0, we get -2, we get 10. In other words, sorry, 1 is not a 0. Okay, well, we got to find something else. So what can we do? We can use the rational zeros theorem. Rational zeros theorem takes a long time, but it's helpful. Rational zeros theorem says we can take the factors of the constant term 10, 1, 5, and 2, and we can write them as numerators in a fraction over the factors of the leading coefficient, which in this case is 1. Okay, that's easy. It's just plus or minus 1. So the rational zeros theorem says if this has rational zeros, they can only be -10, -5, -2, -1, 1, 2, 5, or 10. And so we notice, since this has a leading coefficient of 1, it can only have integer rational zeros. There's not going to be any fractions. So this list is helpful because it can give us ideas for what to try to divide by. We already tried 1. It doesn't work by the factor remainder theorem. So, what can we check? Should I cheat and look at the answer? Nah. I'm going to try 2. That's actually kind of boring. Yeah, I'll do 2 just for simplicity. I think it's going to work, is why I was hesitating. So let me try 2. 2's on my list. So let me do synthetic division. I'll probably speed through this because this video is not about synthetic division. You got to be good at synthetic division, though. Oh, wow, it works. 2 is a 0. So the next thing I would do, I would leave this side, space on the side, as my summary statement so far. I've just found that 2 is a 0, which means we can factor f of x to x minus 2 times this, which is, since it's 4 terms, it's going to be x cubed plus x squared minus 5x minus 5. Now we need to keep factor. We need to factor this. What we can do is just continue synthetic division from here, because we're trying to factor this. So use the same list and continue here. What else is a factor? Let's try 5. Is 5 a factor? I know it's not going to be a factor, but I'll show you anyways. Because when you're doing this, you're going to have to do some guess and check. Now, this is where I wish I would have left more space, but whatever. So look, I can already see it's not a factor. But this is important. Now I can use the upper bound test. The upper bound test says if when you test a 0 and you do synthetic division and all of your numbers down here are positive, that tells you that 5 here, x equals 5 is not a 0, but x equals 5 is an upper bound for my zeros. What that means is that there can be no 0 bigger than 5. The upper bound test literally tells you that if all of your results here are positive when you use that 0, then nothing can be bigger than that. Why is that nice? Because now I know that I don't have to check 10. I can cross it off my list. So the upper bound test helps me cross off some possibilities. So it's a little frustrating that 5 wasn't a 0, but it gave me some information. So I'm going to rewrite where I left off here and try something else. I could try 2 again, but I don't want to. By the way, notice that when we did 2, not only did we find it was a 0, but we can't use the upper bound test for 2 because it wasn't all positive. So that's why I still checked 5. Okay, let's go to the negatives. What about negative 2? Negative 2, let's see if it works. This tells us negative 2 is not a 0. Does it tell us anything else? Well, we can never use the upper bound test for a negative 0. I'll talk about that later. And in fact, it doesn't work as the lower bound test either, which I'll talk about later. It's just, we got to cross it off our list. Let's try something else. Well, let's try negative 1. So again, are you annoyed that it's a lot of guess and check? Maybe, but that's the way it is. So negative 1. Oh, negative 1 works. Good. Therefore, in my summary statement, negative 2 is not a 0. I can write that we have x minus 2, we already knew is a factor. X plus 1 is a factor because negative 1 is a 0. And what we have left is x squared plus 0x minus 5. Now, we could continue using synthetic division, but we would never get another 0 remainder because what this tells us is we can use our algebra 2 skills to say x squared minus 5 has no rational zeros. The only zeros for x squared minus 5, well, you could literally solve this equation. The only zeros for x squared minus 5 are plus or minus, it should be plus 5. And then when we square root both sides, x is equal to plus or minus square root of 5. So we use synthetic division to get 2 rational zeros, 2 and negative 1. And now we've got, let me write this down below. We've got our final answer, negative 2 plus 1, x minus rad 5, x plus rad 5. That's our final answer because we've achieved the goal, and I should write f of x equals that. We've written f of x as a product of irreducible linear factors. Let's break that down. Are these linear factors? Yes, because it's x, 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 x. 4 linear factors equal to a 4th degree polynomial. And it's irreducible. Irreducible means we cannot break it down anymore. I'll probably have to explain that later with another example. But that's it. Let's go to the next one. And then in this very long video, I'll come back and explain later. G of x equals 2x to the 4th minus 7x cubed minus 2x squared minus 7x minus 4. Okay, start with, we know we're going to do polynomial or synthetic division, so 2, negative 7, negative 2, negative 7, negative 4. Factor remainder theorem, is 1 going to be a 0? Well, we get negative 5, negative 9, negative 4. Nope, sorry, 1 is not a 0. So we could do the rational zeros theorem to give us a possible list. Here, the rational zeros theorem tells us we've got plus or minus 4, 2, and 1. Those are the factors of the leading coefficient, or excuse me, those are the factors of the initial value. And then we've got plus or minus 2 and 1 because the factors of 2 are 2 and 1. So the possibilities are plus or minus 4 and plus or minus 2. Okay, I'm done using that. There's no other fraction with 4 in the denominator. Then I use this 2. 2 over 1 is 2. I already got that. 2 over 2 is 1. Okay, and then the only other possibility, since 1 over 1 is 1 over 2. So I always write out the entire list, negative 4, negative 2, because then I can do that crossing out that I showed you when we do the lower bound test and things like that. Those are our possibilities that we need to check. We already found that 1 is not by adding the coefficients. Let's check -1. That's usually a good check. Yeah, you know what? I'm going to see if I can use the upper bound test again by checking 2. So I check 2. So notice I'm like hesitating. What should I do? My strategy is usually to do something kind of in the middle of the positives. Okay, that was not helpful because we found that 2 is not a 0, and can we even use the upper bound test here? No. Since we have some negative results here, we don't even know if 2 is an upper bound. All we know is 2 is not a 0. So we theoretically could have 4. I don't want to check 4. Let me check -2. Maybe it'll give me a chance to explain the lower bound test. Let's check -2. Ooh. Okay, this gives me a chance to explain the lower bound test because what do we see here? We see -2 is not a 0. We get a remainder. But by the lower bound test, x equals -2 is a lower bound of the zeros because the lower bound test says if when you get alternating results, positive, negative, positive, negative, positive, it's switching between positive and negative, then this number is a lower bound for our 0. And what that means is, of course, we found that -2 is not a 0, but it also means -4 cannot be a 0. Because to say it's a lower bound means there can be no 0 less than -2. That includes irrationals. So that was kind of nice. So again, upper bound test, if all the results are positive, this 0 is an upper bound. Lower bound test, if the results alternate between positive and negative, it's a lower bound. That was kind of exciting, I guess. But we still haven't even found a 0. So let's try -1. Yeah, it's a little bit frustrating when it's a lot of guess and check, but you know, at least you're making progress. Okay, now I'm getting really frustrated because -1's not working. Oof. And again, oh, by the way, we could have, if we would have done this straight away, -1 is also a lower bound, but we can already see that here because there's nothing lower in our list. So we just write x equals -1 is not a 0. Will we ever find a 0? All right, let's try 4. 2, -7, -2, -7, -4. Okay, I think we're gonna get it here. 2, 8, 1, 4, 2, 8, 1. 4 is finally. So finally we found x equals 4 is a 0. So the way I write this is if 4 is a 0, x minus 4 is a factor. Result 2x cubed plus x squared plus 2x plus 1. Now actually, there is a quick way to factor this. If you're clever, you can find it out, but I'm just going to keep going with synthetic division. So, not 4. Let me cheat. I know -1/2 is a 0, so let me do -1/2. I would have had a 50-50 shot of guessing that anyways. So we can do fractions, right? So it becomes -2 times -1/2 is -1, 0, 0, 2, -1, 0, boom. So -1/2 is a 0, and we have x minus 4, x plus 1/2 to make -1/2 is 0, and it's 2x squared plus 2. What is that? Oh no. Well, actually, this is good. We can leave it at this. This is the answer. Why? Because the question said irreducible linear factors. Maybe I should have changed the question because we're not going to have a linear factor, but we're going to have irreducible factors. Because 2x squared plus 2 cannot be reduced. One thing we could do, we don't have to, either one's fine. we could take the 2 out of here and put it here to make that look nice. And this would become x squared plus 1, right? Factor out the 2 and give it here. But back to this, x squared plus 1. When does that equal 0? Imagine a parabola above the x-axis. It never equals 0. X squared never equals -1. There's no real numbers that you can plug in there. That's why we call this irreducible. Either one of these would suffice as the answer. So this time we weren't able to get a linear factor, but we did get a linear, and quadratic irreducible factor that's equivalent to the standard form. So, in summary, took 16 minutes to do 2 problems, but we used all of these tools in some sense. It's a process, but once you get better and better at it, it becomes quicker. And there's some other tools like Descartes' rule of signs that I'll explain in another video. Real quick recap. I do want to say one thing. Strategy I could have used here. This one's not very nice because the zeros were -1/2 and 4, so we did have to do some guess and check. But one strategy I want to talk about is factoring. If you look here, you could factor this without doing synthetic division. You should look for factoring rules like difference of squares. If you see something like x squared minus 1, you can factor that. Quadratic, you can use quadratic factoring. Or if you have a 4-term polynomial and this over this, 2 over 1 is equal to this over this, 2 over 1, what you can do is you can do that factor by grouping of factoring out x squared, and you have 2x plus 1. And then here, factoring out 1, 2x plus 1. So, without using synthetic division, you could factor this by saying, oh, we have 2x plus 1, you can factor that out. And you have x squared plus 1, you can have that. So this is still related to the factoring you did in Algebra 1 and Algebra 2. You can still use those tools, but you're combining them with these new pre-calculus tools that we have here. So it's going to take some time. None of these strategies is foolproof. Like even here, right? Here we found 2 zeros that are irrational. So the rational zeros theorem wasn't super helpful to finding those because rational zeros theorem just tells us the possible rational zeros. It could still be irrational. And here we found something that has 2 non-real zeros. There are actually 2 zeros here. If we wanted to factor this over all numbers, we could write this as x plus I times x minus I, because there is a solution to this. It's I and negative I. So summary, it's a process. You got to be comfortable with these rules, and you got to do some guess and check and some exploration. But when you do, it is kind of rewarding, in my opinion, to get to that end at the end there. So keep asking questions, keep practicing. As always, though, go blue.